So like Adam said, I'm Ben Robertson, and today I'm just presenting a very simple model of human hopping that adds on to the data that Dom presented earlier in the session. So let's just go ahead and get started. So what we start with is a very simplified model of the human triceps or Achilles tendon complex. We've got a classical hill-type muscle with nonlinear force, length, and velocity relationships that has a spring in parallel with it, and in series with that entire contractile element is another spring that acts as our biological spring. In addition to that, we have another parallel spring to the whole system that behaves as an exoskeleton. This is manipulating a mass and gravity with a fixed mechanical advantage, very akin to the way you might see the ankle muscles manipulating, during hopping, functioning during hopping. So all the parameters in this model are based off of recorded measurements from humans. And so there are two parameters we're varying here. The first is the activation of the muscle. How can we alter the neural control strategy to best utilize the device? And so we're doing this at a fixed frequency of 2.5 hertz. The second thing we can control is the spring stiffness. So what's sort of the optimal stiffness of the device? And which combinations of muscle stimulation and axis stiffness are actually beneficial? So the first thing we looked at is injury-risk instability, and I'll just go ahead and set up these axes for you. They're going to be here throughout the talk, but on the x-axis we have normalized exoskeleton stiffness, so that's normalized to the passive stiffness of the muscle tendon unit. And on the y-axis we have stimulation that ranges from 10 to 100% of maximum. So the first thing we picked out was injury risk. If we lower our activation too much, we pose a risk of dramatically injuring our muscles. Second thing we looked at was stability, and this is not a contour plot of stability, but suffice it to say the top right-hand corner of this contour plot was unstable. High activation, high spring stiffness was not stable. So we're going to start constructing sort of an optimal operating range for these devices. So on your left, you can see a safe range for operating to avoid injury risk. On your right, we've highlighted the region where injury risk is inherent. And then we've removed stability and done it in bright pink in the right axis. We didn't want to color this whole thing pink. The next thing we looked at was power production. And so one of the nice results I just wanted to show here real quickly is that you can trade exoskeleton stiffness for activation and maintain constant power production. So that would be akin to, say, hop height. You can maintain your baseline behaviors by altering control strategy and adding stiffness. And then we've got the total CE work done and the active work done. So total CE work actually goes up as activation goes down, so as a result of passive stretch. And active CE work is largely activation dependent, no surprise there. The next thing we looked at was metabolic rate. Again, largely dependent on activation. So in picking an optimal metabolic rate, we really just picked metabolic rates that were not super high and that were not posing any, and we're operating outside of a region of injury risk. And our highest metabolic rate, obviously, we wouldn't want to operate at. The next thing we looked at was apparent efficiency of the system. So exoskeleton and muscle tendon unit efficiency, or apparent efficiency, the contractile element as a whole's efficiency, and active efficiency. And we can see here, I guess adding the exoskeleton and reducing activation does make the system more efficient. And that the total efficiency scales about with injury risk, actually. The longer the muscle is, the more passive stretch, the more energy is stored and returned. And active efficiency has sort of this weird contour plot. So, I should say, when picking a region of active efficiency that we really want to target, since active work is really what drives a lot of metabolic cost, there's a nice beneficial range where we can, by keeping activation constant and increasing stiffness, we can actually increase the efficiency of our active element. And at some terminal point, we fall back off. We can no longer increase, we can no longer keep adding stiffness and keep making our contractile element more efficient. So we'll just go ahead and throw these onto our contour. And what we end up with is a region where there's really no disadvantage to operating. You don't see, there's no injury risk, it's not unstable, you've got a good metabolic rate, you've got a good system efficiency, your whole CE is behaving well, and you're utilizing your active tissues effectively. And so I'm not calling this an optimum operating point the way a lot of people have talked about optimization. I'm just kind of throwing this out there as, yes, there is a region where adding exoskeleton stiffness and reducing activation does become beneficial to the mechanics of the wearer. And I'd like to acknowledge the Human Power Lab, Don Ferris and Bruce Wiggin for letting me bounce ideas off of them, and obviously my advisor, Greg Sawicki. And at this time, I'll take any questions.
Same gentleman as before.
Yeah, I wonder, so this optimal stiffness that you predict, is that the same that you believe found experimentally?
So we actually haven't done much experimentally varying stiffness. Dom's experiment only looked at one stiffness, and Bruce is currently studying walking over a range of stiffnesses. But we...
I read something about the sweet spot or the people, I think, presented yesterday.
Was 60%, right? The middle reached to 60%.
Yeah.
What's...
Did you hear about that?
Colleague said that the 60% is difference of the actual name of the best or best decision technique.
Okay, so our optimal stiffness isn't based on purely mechanical outcomes. It's also based on things like injury risk, and inherent stability of our biological system, and muscle efficiency. So yes, you can, from a mechanical perspective, operating with 60% stiffness, if I remember correctly, actually does have some really nice consequences as far as system power outputs are concerned. But from the biological perspective, and from the perspective of injury risk and actual impact on the wearer, it appears a slightly less stiff would be ideal.
Okay, thank you.
Monica?
Okay, so injury risk, I should have said that is peak eccentric strain. So the maximum operating length of the muscle basically during an eccentric contraction.
What do you mean by stiffness?
In this case, it's stiffness in the classical sense, purely just the stiffness of our spring. I'm not looking at any whole joint stiffness here. I'm just saying, okay, well, this is some fraction of the passive stiffness of our system. And when I say passive stiffness, I mean in the absence of any activation.
Benjamin, how do you plan to establish that the region you've picked out here is better than other regions in a practical device?
So there's a couple of approaches we're actually going to take. So we've explored this roof frequency space, and I am comparing the DOMS data. Another approach we're taking is actually using a frog muscle tendon unit in a servomotor setup that's meant to reflect basically limb geometry and inertial dynamics. And so we can add our exoskeleton there and actually observe mechanical changes that might occur as we change the stiffness of our exoskeleton in an animal model. And so there we aren't constrained by things like concern about injury to humans when looking at these optimal stiffnesses, or for optimal stiffnesses.
I also wonder, so in a model, there's something, how much energy is stored in the less elements. Does that compare well with the measurements from the ultrasound that were presented yesterday?
From Dom's talk?
Yeah, I think so.
Okay. I haven't actually compared them, but that would be something worth checking out, for sure. I don't know. I would guess if you found the right set of parameters, you could probably recreate Dom's data, yeah, but...
I'm pretty sure.
Yeah, but so we don't know where in sort of this normalized stiffness space that spring falls. So it'd be tough to make a sort of a blow-by-blow comparison with experimental data. So really what we're looking for is trends that tend to match.
Sorry, I might have missed this, but do you know what the sensitivity of this mapping is, or the spaces for different muscles? Like, thinking like a parallel fibered muscle versus a pennate muscle, are you going to expect different concepts?
So that's an interesting question, and there is no pennation in the model, but that's obviously something you would want to consider if you were looking at this from a human perspective. We just assume sort of a non-pennate muscle in this model, so all our peak strains are relative to that. But if you were to think about this in the context of the actual triceps serrae complex, you have pennate muscles, and they do rotate, and so those operating links that I'm predicting may actually be more damaging to those muscles because they have that pennation. And that's certainly something to take into account.
And I have one last quick question for you. What's wrong with your model? By which I mean, did anything surprise you, and what would you change to make it, reflect what you think should be reality better than it might do now?
So yeah, there are several things wrong with this model. First of all, we've lumped the triceps serrae and Achilles tendon complex, or the whole triceps serrae group together, and made it a monoarticular system. In reality, the gastrocnemiae, which are two of the three muscles in that system, cross the knee. They're biarticular. So that has some interesting implications as far as how this might affect higher limbs, and it also has, it sort of built in a failsafe actually for injury risk. So you can imagine that rather than having only one way to go for our muscle. Now, if it can shorten against whatever's holding it in place and against the load, you may actually see some reductions in injury risk, and injury risk predictions especially. So that's certainly something that I would like to explore further, and adding mass to my muscle. There's no mass in there, so some of the dynamics are a little iffy.
Very good. Thank you, Benjamin.